able to record. Okay, good morning. I'm waiting for my webcam to like zoom out. Sometimes it like does an adjustment. Anyways, all right. So we're gonna start exponential functions and logarithmic functions today. We'll see how far we get. And then I did post a practice test, and it's a real practice test this time. So you can use it to gauge the length, definitely, because I've kept it very, very similar to the actual test. And let me just change this here. Whee, mamma mia. 120. Man, I'm struggling today. Okay, so I posted, so practice test number 2 is on WebAssign. And remember, I'm going to use it as a bonus assignment. So if you do it, that's great. If you don't want to do it, nice. Yeah. If you don't want to do it, then that's fine too. But I'll use it as a bonus assignment, and you do have unlimited attempts, and it's kind of, it's meant to be easy marks, right? So if you wanted to replace one of your kind of lower assignment marks or even missing assignment marks, then this is your chance to do it. So, so have a look at the practice test. I also, because what I had was one of those like mega practice problem or practice tests. So what I did was I boiled it down to be similar to the actual test, which is on Tuesday. And then I took the other ones, so all the other questions, and I made an extra practice. So also see extra practice for test 2. Okay, this is where I put kind of similar problems, right? So if you're having a hard time with a problem, then in the actual practice test, then maybe have a look at the extra practice and see if you can find some questions that are related to those, right? So so the extra practice is just more questions related to the practice test. Because there are different flavors of questions, right? And so I just wanted you to, because what's hard with practice tests is you get so hung up in your mind that these are the exact same types of problems, and in my mind they are, but then you get to the test and you kind of seize up because they're not exactly the same, right? And so so maybe have a look at those extra practice problems just to make sure that you're able to handle those as well, and then you should be good. Okay, so another thing, you do have to submit your work, right, for test 2 again. So I'll be checking your work and just making sure that all the math is sound. So, and then I'll adjust your grade if you know things weren't entered correctly or something in WebAssign, then I'll bump your grade. But if there's missing work, right, then I might decrease your grade. Although honestly, I don't really have the heart to do that. So yeah. Wendy's printer is running hot. It's good. It's way better printing it off. Yeah, or at least I find that it is. So you do have to submit your work. I will be checking your work, but of course all your answers have to go in WebAssign. There will be a lot of questions where there will just be an answer. There won't really be any work. Okay, so so some questions on the test will not require any work. Okay, but you should still write down what answer you're entering in, oh, hey Mandeep. So some questions on the test are not going to require any work, but you should still write down your answer. But you should still record your answer. Okay. Oh, can you hear me?
I don't know if anybody's,
Oh, did anyone else lose me?
I don't know if anybody's lost audio, but I've lost audio for you.
Oh, weird. Oh, you can hear me. You guys can hear me. Okay, that's good.
Okay, now I can hear you. I don't know what happened.
Okay. Just tune me out, don't worry. Oh, weird. Okay, well, anyways, so just keep your work, and even if it's just an answer, you should still record it just in case it doesn't log it in WebAssign, because otherwise I won't be able to give you marks, even if it's right? So just keep it as kind of a record of what you entered. I will say that it's a little bit, it's not long, but it is pushing the entire class time. So, and you'll have the class time to do it, and then you'll submit your work. So you will have 10 minutes after class. You will have until, when do we go till 9:50? So until 10 to submit your work, to submit your written work as a single PDF again, right? Which you've already practiced, so that's good. As a single PDF to Moodle. I'll set up a Moodle Dropbox. Okay, so you will have those extra 10 minutes after class, but you'll only have the class time to do it. So that's 110 minutes. And when you're doing the practice test, maybe keep that in mind, because you'll want to keep your pace up. Okay, it's not too long, but it is like pushing the limits. And if I find that everyone, that no one can make it in time, then of course I will adjust it after the fact. But I ran through it, and you should be able to do it, but I'm just warning you, keep your pace up. Okay, so any questions about the test before we get into exponential functions, which will be on the test, but they're really not that bad. So it's kind of like, it's meant to be easy marks, as opposed to last day. Ugh, rational functions. I'll keep an eye out for questions, but I haven't seen any. So here we go. I'll put it on a fresh page here. So 4.1 is, let's see here, called exponential functions. I knew that. And because there are, like, the notes that I've posted on Moodle, they go through some other scenarios. So financial math uses a lot of exponential functions. And we use terms like exponential growth, or maybe less so exponential decay, but exponential growth is when you have something that kind of looks like this. Whee! Here we have exponential growth. Okay. So exponential functions are functions that have the form a to the power of x. Okay, so you've got some base a and then you've got a power of x. So now the x value is in the power. So here's your x-axis, here's your y-axis. And so exponential growth has f of x equals a to the power of x. Okay. Where a is larger than 1, and we'll talk about what happens if it's between 0 and 1 later. But for now, let's just talk about exponential growth. So exponential growth happens to things like money, right? If you invest money, then it might grow exponentially. Hey, that sounds nice, right? It happens to, well, not to be too on point here, but virus spreads, right? So one person has a virus of unknown sort, and then they meet two people, and then those people meet two people, and then those people meet two people, and even if you only stick to two people, you get this exponential growth, right? And so you kind of start small here, and then as your x increases, it's going to shoot up towards positive infinity, right? So we have this exponential function, and let me just bring in the definition so that we have it proper. Yes. So an exponential function is, like we said, something of the form a to the power of x. So when x is in the power, we have an exponential function. Okay. And so this a is what we call the base. So the base a, and let's see here. A is the base, which makes sense, right? If you're just, what else would you call it? If you're trying to describe a to the power of x, I think you would just maybe land on base anyways. So, but what's important is remembering that for when we move into logarithms, which isn't quite yet, but soon. Okay, so what we said, and I'll just grab it from the handout, is that we could have exponential growth, or we could have exponential decay. Now, let's see here. If you have a to the power of x, so now we're changing it to be, so a has to be greater than 0. So you can't have a negative base, right? Which kind of makes sense because you could just extract that negative and put it outside. But don't worry about that. Just a has to be larger than 0. And a cannot be equal to 1 because 1 to the power of anything is 1, right? So the domain for either of these functions, so here you have exponential growth, and then here, this is what exponential decay looks like, okay? So this we'll call growth, and this is decay. Oops. Okay. So of course they look very similar. So here I've got this horizontal asymptote at 0, right? So this is going to keep going. It approaches 0, but it never actually reaches 0, right? And then what's interesting is it'll always pass through 0, 1 in either case, right? So that's just an interesting fact to kind of log in. And then it's gonna, so for exponential growth, you're gonna take off towards positive infinity, and that's for a larger than 1, right? So if your base is a number larger than 1, you're gonna have growth. If your base is between 0 and 1, so maybe 1/2, then you're gonna have decay, right? So here, let's just highlight these. Right. the base is between 0 and 1, that's when you're going to have decay, right? Whereas in my mind, kind of intuitively, I would say, oh, decay should be negative, but that's not the case. It's going to be a base between 0 and 1. So it tells you the domain and the range for any exponential function. So the domain is the set of real numbers. We can put in any value of x, and it'll still, there are no forbidden values of x, okay? The range is going to go to 0, but not include 0, right? We've got this horizontal asymptote in either situation at y equals 0. So it's going to approach 0, but it's never actually going to reach 0. So that's why we have this round bracket here for the range. And then it's going to go up to positive infinity. So, good. Depending on, and I won't bring this one in, but I do want to look at it. Depending on what the base is, right, the graph of this function is going to change shapes. But look here, all of these are going through 0, 1. So that's an interesting property. And if we kind of analyze it a little bit, right, this is at x equals 0. Well, anything to the power of 0 is what? It's just 1, right? And so that's why everything passes through 0, 1. And I'll make a note of that here. So here, it goes through 0, 1, since a to the power of 0 is 1. Anything to the power of 0 is 1. Okay. So that's always going to be the case. Okay. Okay. So of course, we need to be able to use our calculator to calculate these things. And it's just going to be an exercise of learning how our calculator does exponential functions. So let's just do a quick example here. And let's see here. I want to try. I want to do, let's do 8, just to kind of try those other ones. You have the solutions, right? So make sure that you try them, and because I picked kind of an easier one just to show you guys, but try those other ones just for practice. So f of, I should put it on a fresh page here. Maybe even this. 8. F of x is 3 to the x minus 1. Okay. We can talk about, well, the base is 3, right? And then the exponent is x minus 1 in this case. So f of 1/2 is what? Now I replace my x with 1/2, so 3 to the 1/2 minus 1 puts me at negative 1/2. But what we know about exponents is that that's the same as 1 over the square root of 3, right? We want to always kind of make those connections when we have exponents, right? We know how to deal with exponents. F of 2.5 is 3 to the 2.5 minus 1, putting me at 3 to the 1.5, which, I mean, I'm just going to leave it as 3 to the power of 1.5. Oh, zoot. We were going to use our calculator, not just find these things. We were going to try these on our calculator. That's what we were doing. So maybe I'll scratch this. Because how we're going to find it on our calculator is this guy. I don't know what I was thinking. Okay. Oh yeah, we know how to solve it. But do we know how to find the answer? So I'm going to use the Desmos calculator. I don't really recommend using your phone calculator. Like if you've got an iPhone, it's the calculator is fine, but it doesn't really work for me. So maybe have a different calculator. Even a real calculator would work. But a lot of calculators have different ways of doing these exponential functions. So just get to know your calculator of choice and then work from there. So we want to do 3. And then if I want to do to the power of anything but 2, I've got this a to the power of b button. Right, I'm trying to hold it down here. Oh, well, I guess that highlights it a little bit. So if I do a to the power, oops, I hit the wrong button. A to the power of b, notice how it puts the cursor up in the power. So now what I want to do is I want to make sure that my -1/2 is all in that power, right? And so just to make sure, you can kind of keep an eye on it because in this calculator, it shows you where things are going, right? If it's staying in the power, if it's bumping it down. But just to make sure, I would wrap this up in brackets. And then just notice that I step it out, because then I can be convinced that this is all staying up in the power. So I get 0.57735. And I do wish I could copy this, but I can't. So I'm just going to do it on the side here so I can write it out. 3 to the, okay. I'll do squiggly equals because as soon as I'm working with a decimal, it's not exact anymore, right? So that's when you use your squiggly equals. So 0.5773502,692. So make sure that you get that same answer, right? So if I do 3 to the power of 1.5, make sure that you get 5.196152423. Or it should be the same. Okay. So make sure that you're okay doing those calculations on your calculator. We'll only do those 2. How about? Because I want to move on to actually making this equation. So if you have a graph and you can see that there's exponential growth or decay, right? So you have this exponential function, then you know it's going to have the form of a to the power of x. And then if you're given a point anywhere on this curve, well, that's an xy coordinate, right? So that's an input-output coordinate, and you can use that to find the equation of the actual graph. So let's just pick one here, do 23. I guess I didn't bring in the whole question, but here it is. I cheated. There we go. Delete, paste, there, nothing happened. So we want to find the exponential function. And remember, f of x, you can just read as y, right? So f of x equals a to the x. So now, but you have an xy coordinate, right? And so that's what you're going to use to find what this a is. Okay, so let's do 23 together. So I have f of x equals a to the power of x. And we're given it goes through the point 2. So when x is 2, y is 1 over 16. Okay. So what we have is we have f of x equals a to the power of x. So the output is 1 over 16 when x is 2, right? And so what we have is we have 1 over 16 is a to the power of 2. Okay. We've already talked about exponents, right? So we know how to undo this exponent. We do that by taking the square root, right? Because if it's to the power of 2, how do I kind of dissolve that? Well, I take it times a power of 1/2, right? 2 over 2. And so we can take the square root of both sides is the square root of a squared, but we actually need the plus minus version of it, right? As soon as you take a square root of a square, you get a positive and a negative. Now, we do have that condition that a has to be greater than 0. So we're only going to look at the positive one. So if you forget it, it's fine in this case, but in general, it's something that we have to remember. So then here, what we found is that a, and I'm just kind of swinging these around, right? Remember, the equal sign is just a revolving door. And when I take the square root of a squared, I just become a is going to be the plus minus root of 1 over 16. So this becomes plus minus the root of 1 over 16. But since a is greater than 0, right, it has to be, we only consider the positive one. So then what we have is we have a is the root of 1 over 16. Again, we have to go back to our exponent laws. No surprise, we're doing exponential functions, so we are drawing a lot on our exponent laws. And if those are a little bit rusty because it's been a little while since we worked on them, maybe go grab them from before. I can't even remember what section we did that in. Might have been somewhere in chapter 1, probably. Yeah, I feel like it was 1.2, way back. All right. But I can split this because I'm dividing inside. This is the same as the square root of 1 over the square root of 16. But the square root of 1 is going to get long, even though it doesn't have to be. Square root of 1 is 1, and the square root of 16 is 4. Okay, so now I have that a must be 1 over 4. Does that make sense? Well, yes, because we already know from the graph, right, that we have exponential decay, right, because it's going down. So we've got this decay function, and for decay, we're expecting our a to be between 0 and 1. So 1/4 fits the bill, right? And so far things are checking out. A is between 0 and 1 since we have decay. Okay. So therefore, f of x is a to the power of x, which is going to be 1 over 4 to the power of x. Okay. And then that's your function, 1 over 4 to the power of x. We just leave that x open, right, because it can handle any value of x. So try those other 3 on there. Again, you have the solution, so you've got something to work towards. But being able to develop that function, you'll see, is also on the practice test. So might be good. Okay. So in general, exponential functions have the form a to the power of x. We're going to talk about the natural exponential function, which uses e as the base. Let me see. Oh, I did have, let me see here. This is important. I did have an exponential decay joke. So the thing about exponential decay is you've got this horizontal tangent line, right? So you're always going to be approaching zero, but you can keep cutting things in half, right? And in the beginning, cutting things in half, right? So the half off haircut, right? That's a lot taken off immediately. But then, you take the other half off, and then you take another half off, and then you take another half off, and then you take another half off. And in theory, you can do that an infinite amount of times. So, so this is going to take forever. In theory, it would. You're going to reach a point where it's going to be negligible, but in theory, you can keep cutting things in half, and that's exponential decay. So, anyways, I just thought that was really cute. So, anyways, there's that. I'll put it on the next page. 4.2 is kind of a special case of the exponential function. It's the natural exponential function. So the natural exponential function is still f of x equals a to the power of x. Now notice something that I want to just articulate, because we can recognize quadratic functions, right? We can recognize linear functions. We can recognize polynomial functions, right? We can recognize rational functions. And we also have some idea of their graph or their overall graph just from those, from the type of function that we have. So now I want you to add this one to your roster, right, of anything with an x in the power or in the exponent, kind of helps you remember, is going to have that growth or decay shape, right? So you'll know the shape of this graph just by looking at a function like this. Now, the natural exponential function is no different. It's just a special case of where a, so the base, is e, which is Euler's constant, which you don't need to remember, but it's an irrational number, just like pi, kind of not as well known. Depending on your field of study, you use it a lot, right? So the natural exponential function is a special case of f of x equals a to the power of x, where the base is e. Now, e is an irrational number. E is roughly 2.718, blah, blah, blah. There's a song, 2.71828, blah, blah, blah. Anyways, doesn't matter. Just like we know pi is roughly 3.14. I'll be so embarrassed if I screwed that up. Anyways. No, I won't be. But just like we know pi keeps going forever and ever, just like pi, e keeps going forever and ever and ever. So e is an irrational number. So I'll just clarify, keeps going forever. Forever, like pi, right? It's just another irrational number. And so what we do is we use the E button on our calculator. Just like you have a pi button, right? Somewhere on your calculator, you will find pi. So we use the E button on our calculator. Of course, if it keeps going forever and ever and ever, your calculator is using an approximate value, but it's got it stored to some specified number of decimal places where we decide, oh, okay, that's good enough. So to do something like e to the power of 4 on your calculator, so try, oops, that doesn't say try. Try e to the power of 4 on your calculator. E to the power of 4 is going to be roughly, and let's see here. So depending on your calculator, let me just clear this. In the decimals calculator that we're using here, or that I'm using here, it's not in the main menu. It's going to be in the the function menu, and kind of over in the right hand column, you've got an e to the power of x button. Okay, and so you also have e, right? So you could just use e and then raise that to the power of something, or let's just try using the e to the power of x, and then it just bumps you up into the power anyways, as opposed to just hitting e and then you can do maybe 3 times e or something like that. Right, so depending on what you need it for, you can use either one of those, right? And so e, you have to use the e button, and sometimes you even have to type in things like exp and then in brackets, but you'll know it if your calculator behaves that way. So I want to do, let's see here, I want to do e to the power of 4. So I'm going to use that e to the power of x button because I want to raise it to the power of 4. So here, and I get to roughly 54.59815,003. Okay, I'm going to have to do it on the side here so I can copy it out, just so you can check your answers later. E to the power of 4. Okay. Roughly 54.59815,003. So just make sure that that's what you're getting when you try e to the power of 4. In Desmos, I just want to show you the graphing calculator. Maybe that's where I'm thinking of the exp. Let's see here. Let's try to graph e to the power of x. So in your functions, you've got trig, stats, dist. Let's use misc, miscellaneous. Oh yeah, so here's your exp. Here, I knew we had to use exp. So exp, and then what it wants is it wants exp and then in brackets the power, typically. I wonder if we can use to the power of x. No, it doesn't like that. So then bracket x, it does like that. So just like all the other exponential growth functions, right? It's just a special base. It behaves the same way as all the others. It passes through 0, 1, and it's just got some really nice properties that we use later in calculus. Okay? So that's why the e to the power of x is our exponential function of choice. Okay? But notice that, so because e is between, let's say, 2.5 and 3, because it's 2.71828, right? So if I graph 2.5 to the power of x, oops, didn't do the power, to the power of x, right? It's going to wrap around it. And if I do 3 to the power of x, it's going to wrap around it on the other side, kind of like snakes around it. But notice, right, we could get close to e to the power of x just by changing our base to be closer and closer to 2.71828. The song will come to me soon. No, that's okay. I'd rather not. Let's see here. All of which will pass through 0, 1. Okay. So on Desmos, to graph e to the x, that's what I want to say. To graph e to the power of x in Desmos, use the exp function. And do exp and then no space, right? It's exp of this thing of x. Yeah. And maybe I'll go back, I'll just take a screenshot here. Try to hit the right buttons. Cha-ching. Just so you can see how I entered it. Okay, good. So the natural exponential function is going to be our go-to exponential function. But like I said, all the exponential functions behave the same way. Oh, hey. I should bring in the definition here. So if you have an exponential function base e, what's important is that it's often, so we use it so much that it's often referred to as the exponential function, right? So it's the one that we want typically. Okay. So let's see here. There is a couple of examples, or there are a couple of examples here walking you through just how to do some of these problems. So I don't typically have problems worked out, but in this case, I wanted to have some that you can kind of rely on. I want to do question 23. Okay. But definitely just to get used to working with a calculator, we've already done some of these, but definitely work through these calculator problems, right? Finding e to the negative 3x, where x is maybe negative pi, right? Really kind of upping the ante. And remember, you have the solutions, so you can check your work, but make sure that you're getting the same answers. And hey, look, it's the same graph that we just did, but we just kind of winged it, right? Cool like that. So I do want to talk about this question here. So when a certain medical drug, and this is the case for drugs, of course. It's also the case for kind of radioactive materials, anything that kind of decays over time. Even things like plastic, right? It's going to decay. It's going to be really, really slow, but it'll have some sort of decay model, right? As well as, other things will have growth models, but in this case, we're talking about drugs. So when a certain medical drug, I love that they specify a medical drug. When a certain medical drug is administered to a patient, the number of milligrams remaining in the patient's bloodstream after T hours, and you can imagine, blood alcohol levels is going to be really common to talk about, drugs, all those things, but they all behave the same way. They're just going to have different models, right? So it's going to be modeled by, sorry, well, must be the end of the week when I'm kind of losing my voice here. So D of T is just going to be the number of milligrams remaining. I don't know why it's D of T, but it is. It's going to be 50 times e to the negative 0.2 t. Now t, right, is, yeah, let's do this example and then we'll have a coffee break. How about that? I promise. So then negative 0.2, remember the negative actually bumps the e down to the denominator. So it's actually 50 times 1 over e to the 0.2 t. We don't need to worry about that, but that makes our base between 0 and 1, right? So just kind of explaining why it's decay. How many milligrams of the drug remain in the patient's bloodstream after 3 hours? Now, some things to keep an eye out for are the units, right? So T hours, and we want 3 hours. If it said after 20 minutes, you would have to convert those 20 minutes to hours, right? Which is what, 20 over 60, 1/3. So T is 1 over 3. But we've got a nice breezy example here. So D of T, I'll just write out the answer or the model here, 50 e to the negative 0.2 t. And D of T is the milligrams remaining after T hours. Oops, after T hours, right? So what we want to find is we want to find D of 3, right? How much is remaining after 3 hours? So we have 50 e to the negative 0.2 times 3. What's key here is you want to find e to the negative 0.2 times 3 first and then multiply it by 50. So I'm going to show that, or each step of the calculation, I'm going to show kind of evolving here. So 50 times e, I'm first going to do 0.2 times 3 is, of course, negative 0.6. I did check it though. So now the next step is going to be doing e to the negative 0.6. And then I'm going to multiply it by 50. So let's just go to our calculator here. And we want e to the power. So that's e to the power of, and I want negative let's do 0.6 just in case. It shouldn't matter. So make sure that it's showing exactly what you want it to show. Okay, and I'll do it over here so I can copy it down. Okay, good. I get the same same thing. So then this becomes 50 times 0.5488116,361. So then I can go back and now I can say, let's do another one. 50 times, and then how do I do the previous answer on here? Oh yeah, see the ANS button? It's down here by the plus. I use that all the time where I insert the previous answer. So it'll just take the most previous answer, and insert it, right? So I use that a lot. Okay, and it'll even show you what it is, what the previous answer was, just in case. So here we have our final answer, and I'm just going to do it on this side here. And I get the same thing. So I get roughly 27.4405818. And what is this? Well, after 3 hours, we would have 27.44 milligrams left in the patient's bloodstream. Milligrams remain after 3 hours. So not bad, right? Let's have a little break. We'll go until kind of 9:01-ish, just for a little buffer. And then that'll be good. Grab some coffee. Break until 9:01. 5 minutes. Let's get going, shall we? Okay, so for what I'm expecting you to do, right, I'm just going to give you the function like this, and then you're going to use the function to evaluate it, right? So I'm going to give you some input, so t is 3, and then you're just going to find what the output is. Okay, so we're not going to do stuff like build this model, even though, I mean, we could go down that rabbit hole and talk about how do we build this model, but I'm just going to gloss over that. I'm just going to give you a model and expect you to be able to plug things in and use it. Okay, so let's see here. I can remove this. Delete. There are some more examples on the handout, and kind of peppered throughout, definitely in just the 4.1 handout, there is a note about compound interest, which might be fun to look at as an example just for life reasons, but I'm skipping it because I didn't put it on the test, so you don't need to worry about it for the test, but it might just be nice because it's how most interest is calculated for kind of bank accounts or Visa cards or whatever financial thing you're looking at. There's also continuously compounded interest, which is on the second page, which is also kind of interesting, but it's not very common. So again, I'm just going to skip it because I didn't put it on the test, but it is there if you wanted to kind of exercise your business math skills. Right? And there's a whole course on it. If you take Math 114, this is all we do. Compound interest, continuously compounded interest. It's not all we do, but it's most of what we do. And I'm teaching that right now as well. So maybe I'm sick of it. No. Usually I like to do it with this class, but I do want to get going to logarithms. So logarithmic functions, and I even gave the spoiler alert last day, logarithms are just the inverse of exponential functions. So we can start by looking at an exponential function. It doesn't actually matter which one. I'm giving a lot of blank space here. Okay, that's okay. 4.3 is on logarithmic functions. Okay, so from the graph of an exponential function, we see that it's one-to-one. Remember, to have an inverse, it has to be one-to-one, which means it has to pass the horizontal line test, right? And so from the graph of an exponential function, and remember, they look the same, right? So it doesn't matter which one. So from the graph of an exponential function, we see it passes the horizontal line test might be a good refresher for, because that's on this test coming up, right? Inverses is something one-to-one. It has to be one-to-one to have an inverse. So it is a one-to-one function. This means it has an inverse. And we've solved for the inverse, right? We rearranged, we solved for x, and then we replaced our x's with y's, and then we had our inverse function. What's hard is that, okay, well now our x is in the power, so we don't really have the tools yet to bring that down. And so, but I'm just going to tell you that the inverse is the logarithmic function. So the inverse of an exponential function is the logarithmic function. Okay. So let's see here. Oops. This one. I'm going to grab this blurb here. And I want to talk about it because it can be really confusing. Okay. Or maybe that's just me, but I find that the relationship between logs and exponential functions, it takes a lot of practice, right? And so what it says is that if you have a to the power of y is equal to x, right? So here you have this exponential function, then what that says is that that's equivalent to log base a. So notice we've got that same base, right? And so here, let's just kind of talk about log base a of x equals y. You're going to read this. Maybe I should use a different color here. Read log base a of x equals y. Okay. And what's key here is that you have this base a. Okay. Is equivalent to a to the power of y equals x. So, which again, we have a base a. Base a. Now, here's where it gets weird, right? Here you have this y. So a to the power of y equals x. Okay, so in my mind, at least what I have to do is that's how I have to read it. A to the power of y equals x. So let's just kind of write that down here. Log a x equals y. So here's kind of my step one, a to the power of y So this is kind of my first step. And then my second step is kind of going this way. Equals x. Okay, so a to the power of y equals x. Right, that's how I establish the relationship between log base a of x equals y. Ooh. Okay. So what I want to do is I want to take some of those exponential functions and I want to rewrite them as logarithms. So I'm going to go back to, let's go to 4.1 and grab some exponential functions maybe. Oops. This is from, from 4.1. Rewrite these as logarithms. Okay, so let's see here. 7 is really y equals 4 to the power of x. Okay, so all right. The base, I think we can all agree that the base is 4. So that's a good start, right? And maybe it's easier if I rewrite my function, my exponential function, in the same order, right? Because then I can kind of see the relationship. So maybe it's easier if I write 4 to the power of x equals y. Because now I need to rewrite this into a logarithm, okay? And so what I have is I have log base a, which is 4 in this case. Log base 4, so that base came from there. So same base, right? Log base, exponent base, we call them the base regardless. And then whatever's in the power, it actually moves to the other side of the equal sign here. So in this case, the power is x, and whatever is on the equal side, so y in this case, moves into the log, right? Which log base 4 of y equals x. If we think about it as an inverse, right, it will have that relationship where, okay, if you take the inverse of something, the x's and y's are essentially going to shift around. So log base 4 of y equals x is the same as 4 to the x equals y. So now these are equivalent statements, but it just depends on how you want to write them. So let's go on and do 8. You've got, and I'm going to rewrite them, 3x minus 1 equals y. Just to use that same order again. So I can see already that my base is 3. Okay. And so log base 3 is where I'm going to start here. So I've got log base 3. And then remember, the power okay, becomes on the other side of the equal sign, and then the x is going to move inside. So what I have is log base 3 of y is equal to x minus 1. Okay. Notice that what we're doing is we're able to bring down this power, right? So otherwise we don't have any way to solve for this x, right? So here, notice by rewriting as a log, we are able to bring down, and that's obviously not a technical term, but we're able to bring down the x from the exponent. The x from the exponent. Probably to solve for it. Right? So eventually you'll probably want to solve for x, right? And so one of the ways that you can do that is to, or the way that we will do that definitely, but for now it's going to seem kind of mystical, is taking the log. So we need to take the log to bring down powers if we're solving for the power. But for now, we're just going to focus on rewriting these logs or these exponents in terms of logs. So let's do 9. I've got 1 over 3 to the power of x plus 1 equals y. Again, I've got a log of 1 over 3 of y equals x plus 1. I'm moving a little bit faster. So I know that this is going to take a lot of practice. It's taken me years of practice to actually kind of have this rhythm, right, of rewriting an exponent as a log. Otherwise, I used to have it on like a scrap piece of paper somewhere when I was doing my homework and that kind of stuff in the beginning. So definitely take your time and figure out how to rewrite these exponents as a logarithm. I'd argue that rewriting the log in terms of an exponent, right, which is moving the other way. So if I give you something like this, can you something like this, can you rewrite it like this? Right? And so that's when I just read it like this, a to the power of y equals x, right? And then you can kind of have that rhythm. Okay? But let's do 10, which is what? 4 over 3 to the 3x equals y. My base is 4 over 3. So I have a log base 4 over 3. We don't really use log bases that are fractions, but can, I guess. So the log base 4 over 3 of y equals 3x. But here you would be able to solve for x, right? And so that's the goal of taking logs typically. Okay, so I want to make sure, do I have the change of base formula on here? Where is it? Okay, no, not yet. All right, so kind of moving the other way around. Let's evaluate these logarithms. So I want to practice the other way by rewriting it as an exponent. Okay, so here I'm going to specify, evaluate the expression by rewriting the log as an exponential function. oops. Because that's going to be the easiest way to do this. So now we have something of this form, right? Log base a of x equals y, and we want to solve for y, right? So let's start with, let's do all the a's, how about? 25a. Because then we get a nice variety here. So we've got log base 2 of 2 equals y. Let's call it y. Right? And we want to solve for y. Okay. Now I'm all hung up on, where's that change of base formula? Let me just try to find it so that I know. Okay, it's not until 4.4. Fine. All right. So what we want to do is, if we want to solve for y, remember our kind of chain here, 2 to the power of y equals 2, right? So I'm going to rewrite this as 2 to the power of, and maybe I'll use green, 2 to the power of y equals 2, right? Because, and it's confusing, we'll move away from digits of the same kind here, but 2 to the power of y equals 2. Okay, so 2 to the power of what equals 2? Well, 2 to the power of 1 equals 2. 2 to the power of 1 equals 2. Therefore, y is 1. Okay. Let's go ahead and do 26a. Log base 3 of 3 to the power of 7. And I want to know, what does it equal? I'll call it y. So now, right, 3, remember our chain here, 3 to the power of y equals 3 to the power of 7. Well, right, so I always find that going from a logarithm to an exponent is a lot easier for some reason. Probably because I can see it, right? 3 to the power of y equals 3 to the 7. Even though it's not intuitive, I can still follow that kind of circle. And so here I get 3 to the power of y equals 3 to the power of 7. So y must be 7. Which means that the log base 3 of 3 to the 7, even though that looks tricky and complicated, right, we know it must be 7, right, from here. Okay. How about 27a? Log base 6, log base 6 of 36 equals y. So now I have 6 to the power of y equals 36. Again, it's not that bad to have to solve for that y. You can try different values, but I think you'll find that 6 squared is 36. 6 times 6 is 36. So we've got 6 to the power of y equals 36, right? And we can try 6 to the power of 2, right? 6 to the power of 1 is 6, so we move on. 6 to the power of 2 equals 36. Therefore, y is equal to 2. how about 28a? Log base 2 of 32. Log base 2 of 32 is equal to some y. So 2 to the power of y is equal to 32. Now you might have to try a couple of different values, right? So try, if you don't know immediately, right? Try 2 to the power of 1 is 2, nope. 2 to the power of 2 is 4, nope. 2 to the power of 3 is 2 times 2, so 8. 2 to the power of 3, let me just check. 8, no. 2 to the power of 4 is 16. Oops. So sometimes, right, you might have a good jumping off point. Right here, I wouldn't have started with 2 to the power of 2, for example, because I know it's 4, right? But I just want to show you that sometimes it's trial and error that's going to get you there. 2 to the power of 5, ding, 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 is 32. Therefore, y must be equal to 5. So then the log base 2 of 32 is equal to 5. Okay. Good, good, good. So for our domain of logs, so for our kind of roster of domains, right, we know we can't divide by 0, and I can't take the square root of a negative number. I can take the square root of 0, right? So that's the difference between what I'm about to, you won't believe what happens next. Dun, dun, dun. So for the domain of logs, we have, we can put in any values of x, or any input into any log, but it has to be greater than 0. So it can't go and be 0. We can't take the log of 0 or a negative number, which we can see if we look at the graph of, well, definitely an exponential function, but I guess we haven't really seen a logarithmic function. Let me just bring that in. It's way down here. What's it doing down there? It's the inverse of a function, so it's reflected. So it's the exponential function reflected on the y equals, or x equals y axis, kind of on the diagonal. So here, right, we have an exponential function, and then the inverse is the logarithmic function. And what happens is we can have any value of x put in here from 0, but not including 0, and then up to positive infinity. So notice the domain for logarithmic functions is from 0 to infinity, right? And so what happens is we need to add this to our roster of checking for domains, right? We need to add this to our list of rules for the domain, right? So remember our domain rules. Number 1, we can't divide by 0. Any value that makes you divide by 0 has to get pulled out of the domain, right? So we can't divide by 0. I can't take the even root of a negative number. Can't take the even root of a negative number. Oops. Right? And then now, kind of new. Now we have a third thing to look out for when we're finding the domain. So we can't maybe it's easier if I say we can only, so now I'm kind of changing the setup here, can only take the log, and that's the log of any base. It doesn't matter what the base is, but we can only take the log of a positive number. Not including 0. Right, we can't, you can try it on your calculator, but it's going to throw a hissy fit, right? If you take the log, so let me clear all here, the log buttons are in the func section, okay? And we've got the log here, so if I take the log of, if I try to take the log of 0, it's going to tell me that it's undefined. What if I try to take the log of -1, also undefined? Let's try the log of 1, it's 0, okay? Think about that relationship for a second, right? The exponential function always goes through 0, 1. Anyways, you can kind of make the connection there, but it's not something I want you to focus on. Right, but so the calculator will tell you, hey, I can't do that, but it is something that we need to think about when we're finding the domains now. So now we need to add that third thing to keep an eye out for, right? We're looking out for division, can't divide by 0. We're looking out for roots, square roots specifically, typically, and now we're looking out for logs, right? We need to adjust on the logs. So what we're talking about here is called, so this log that we used, oh, it's been cut off. It's okay. Log, the log button that we used, log base 10, is the common logarithm. So there are 2 logs with special names and with special bases that we don't write. So whenever you see just a plain old log of x, it means log base 10. Okay, so writing just log means log base 10. And it is called the common logarithm. The other one that's also got a name is the natural logarithm. The natural logarithm is log base e, and we actually changed the writing of it to just be ln. So here, let me see here. I think I made that too big because I want to keep it all on the same page here. So now, right, these are the 2 logs that have special names. So the common logarithm is log base 10, and the natural logarithm is log base e. So what we do is we write ln for the natural logarithm, or logarithm natural, I guess. Here is kind of an annoying thing that I can't quite seem to tame. Because the only log that we use in statistics for sure, where I kind of come from. In most sciences, the log that you will be using is the natural logarithm. So I have this really bad habit of whenever I see ln, I just say log, and that can be really confusing, especially if you're just learning this stuff. But I do want to point it out in case I let it slip. I try to say ln, but if I say log, I probably mean the natural log. The only guys who use, and by guys I mean fields, the only fields that use log base 10 are, I think, sound. So like engineering, sound engineering. Sound works in base 10. Computer programming works in base 2. We're not going to go there. And so, but for most sciences, the log that we use is log base E. So in most sciences, the log we use, and I guess I should say logarithm we use, is the natural log, which is log base E, which we write as ln, and I also write it as this kind of script ln, and that I cannot get away from. So we use a lot of natural logs, and so that's why I've developed all these kind of bad habits. So I just need you to know what I mean when I write this little ln scribbly ln. It's the natural log, and sometimes if I say log, I probably mean the natural log. Okay, so it's just the log base E. There's nothing really special about it, but we should talk about kind of what it means. Right? So now if you go to your Desmos calculator or any calculator, if you go to the functions again, you'll see that there is an ln button, right? The ln, okay. And clear all there. If I take the ln of, it has the same properties, right? So it has to be greater than 0, not equal to 0, right? So if I take the ln of 4, for example, it gives me a number 1.38629. So just remember the ln of 4 is the exact value, and then the 1.386 whatever is the approximate value. Often WebAssign wants the exact value, right? Unless it specifies. Okay, let's do some domain work here. So remembering that the domain of logs, we have to have inputs that are greater than 0, right? And it doesn't matter what the base is, right? Here we've got a log base 10, that's a common log. Log base 3, no name. Log base 5, no name. ln, natural log, right? So, but it doesn't matter what's going in here. It has to be greater than 0. So let's do 76 just to practice with those natural logs. So g of x is the ln of x minus x squared. Let's just highlight that, okay, well, this means that x minus x squared has to be greater than 0. This actually looks kind of familiar, right, from when we looked at inequalities, right? So what I can do is I can factor this thing, I can factor out a common x. So I get x times 1 minus x has to be greater than 0. What does that mean? Well, this thing is going to be greater than 0 if both of these are positive or if both of these are negative, right? So you have to kind of keep track of those, right? And we use the number line to figure out where this thing was positive. Let's see if there's another way that we could do it. X has to be greater than x squared. Hard to visualize. So let's just go ahead and use this one. So here, what I want you to notice is that this will be positive if x is greater than 0 and 1 minus x is greater than 0, or if x is less than 0 and 1 minus x is less than 0, right? Inequalities are kind of tricky that way. So, okay, so x is greater than 0 and 1 minus x is greater than 0. Well, this we can kind of morph to 1 has to be, greater than x. So x has to be less than 1 and x has to be greater than 0, right? So between 0 and 1. And here x has to be less than 0, and then just kind of reworking this inequality. 1 has to be less than x. So x has to be between x has to be less than 0 and x has to be greater than 1. It can't happen, right? Because they both have to happen at the same time, right? So x here is larger than 1, but it also has to be less than 0, so that can't happen. And so here, x is greater than 0, but x is less than 1. So from here, x is between 0 and 1 is the domain. You would have gotten there if you had rearranged this x minus x squared has to be greater than 0 as well, right? Moving, so adding x squared to both sides, x has to be greater than x squared. That only happens if x is between 0 and 1. But this way is kind of more dependable. Let's do another one. Let's do 78. Just for a mashup of not just logs, right? So here, I know that x minus 2 has to be greater than or equal to 0, but I also know that 10 minus x has to be greater than 0. Notice the difference, right? I can take the square root of 0, but I can't take the log of 0. So, and then I'll put an and here because both of those have to be true. Both of those have to be satisfied. Now, let's see here. So I have x minus 2 is greater than or equal to 0. So x must be greater than or equal to 2. And 10 minus x has to be greater than 0. So 10 must be greater than, x. Kind of flipping these around, right? I've got x has to be greater than or equal to 2, but it has to be less than 10. So then the domain is that x is greater than or equal to 2, but less than 10, right? Or if you prefer 2 to 10, round bracket. Okay. So now, last thing I want to do, and I know I'm pushing you guys hard, but these are all just kind of, hopefully, kind of quick skills. we're going to use the definition of a logarithmic function. So remember, the whole goal was to be able to solve for x. And so let's use the definition of the logarithmic function to find x. So let's do 35a. Oh, reminder. I have log base 4 of x equals 3. So remember how we rewrite this? 4 to the power of 3 equals x, right? So we're going to rewrite it as an exponential function in order to be able to solve for x. But, right, so this means that 4 to the power of 3 equals x. Well, 4 to the power of 3, I'm just going to do it over here. But 4 to the power of 3 is 64. Right, not bad. How about let's do 37a with that natural log. I'll put it here so I don't have to scroll around. 37a, I've got the natural log of x equals 3. This as an exponent, right? Even though we don't see the base, we know it's base e. So you have e to the power of 3 equals x, right? The base is e to the power of 3 equals x. So e to the power of 3, I'm just going to do it on the side here for ease. E to the power of 3, I get roughly 20.08553692 is approximately equal to x. So you can use the definition of the logarithm to rewrite it as an exponent or an exponential function, and then it's easy to solve for x. Now, let's do 37b because I see that it's a little bit different. I have the natural log of e to the power of 2 equals x. Okay. So when I rewrite this, I have e to the power of x equals e to the power of 2. Well, right, because this e to the power of 2 is not in the base. It's all inside the log, right? So the log base e to the power of x equals e to the power of 2. Therefore, x must be 2. All right. Last, I know I'm pushing it here, but the last example, and then I'll be so happy, is this bacteria colony one. And the reason I want to do this one is because I have put a bonus question on the test, but wouldn't it be uncool of me to not have done one like it? Wink, wink. So we've got a certain strain of bacteria divides every 3 hours. So if a colony started with 50 bacteria, then the time in hours required for the colony to grow to capital N bacteria is given by this function. So of course, kind of later courses, you would build this model given this information. But now I'm just giving it to you. I want you to find the time required for the colony to grow to 1 million bacteria. So N is going to be 1 million. Right. So here, N equals $1 million. And you want to find the time required. So T is going to be 3 times the log base 10, right? If I have just the log of 1,123,123 divided by 50 over the log base 10 of 2. So what we're going to do is we're going to simplify inside the log first. Okay. And then I'll take the log of that, and then I'll divide it by the log of 2, and then I'll multiply it by 3. So it's just a bed mass problem in the end. So we've got 1,123,123 divided by 50 is 20,000. So then I'm going to start a next line, and I'm going to take the log of that previous answer. So I'm going to use that answer button again. Okay. And then I'm going to close that bracket, and I'm just going to go for it here. Divided by, again, I want the log of 2. So always making sure that it's behaving the way you need it to. Okay, so that's 14.2. And then I have to times that. So that previous answer times 3. And then I'm going to screenshot this, bring it in. Crop this. Okay. So then the time that you would need is roughly, it's just an approximation, 42.86 hours. I know I went over time, my apologies, but that one, it's for a bonus question. 1 mark. So it was worth it. Any questions before I let you go? If you do have questions, if you're working on the homework or whatever, then definitely feel free to just text me or email me, and we can work through some problems. But also you can make use of the Learning Center, which Kate introduced last day, if you want to. Anyways, if you don't have any questions, see you for our test on Tuesday. I'll be here if you have any questions during the test. You don't have to be in the Zoom room, but I'll be here. See ya. Happy studying.